Hi, in this video we are going to discuss the concrete pseudocode for the Dijkstra shortest path algorithm. So let's get started. First of all, we have to create a distinct class storing the information about the node. For example, the name of the node, the minimum distance from the starting point to the given node. It's going to be so the min distance is going to contain this information. Then, in order to be able to construct the shortest path tree at the end, what is the shortest path tree? The shortest path tree is a tree-like structure. The root node is the starting vertex, and it's going to show us the shortest path to every other vertex in the graph. So we can reuse this tree-like structure. That's why it is very beneficial to construct it. So we have the name, the minimum distance, so the distance from the starting point from the root node, and the predecessor. Basically, the predecessor is the previous vertex in the shortest path tree. Okay, so it's going to tell us that from what vertex we came here. Okay. Basically, this is the pseudocode for the algorithm itself. We have a graph and we have a source vertex. Of course, we have to define that from where we would like to calculate the shortest path. The distance for the source is equal to 0 because we are standing there, and we create a queue storing vertices. The name will be Q. Okay, we iterate through every vertex in the graph. We set the distance equal to infinity. This is the so-called initialization phase. Distance from the source is 0 because that is the starting point, and all the other nodes' distances are infinity because we don't know the distance in advance. So it is unknown. Basically, the infinity is a guess, and because no number is greater than infinity, it is a good guess. Then we set the predecessor for the v to be equal to undefined, so the previous node in the shortest path is not known in advance. And we add every single vertex of the graph to the queue. So we have this queue, priority queue, abstract data type. Then we have this while loop, as we have seen for breadth first search and depth first search. While the queue is not empty, we are going to get the vertex from the queue with minimum distance. This is why to use heaps, because for heaps we know for certain that the minimum item is at the root node. So it is order 1 constant time complexity to get the minimum item, plus we have to reconstruct the heap in logarithmic time complexity. And basically this is why this logarithmic time complexity is going to yield the linearithmic time complexity as a whole for Dijkstra's algorithm. So if we wouldn't use an appropriate data structure, a heap for example, then the running time would be worse. Okay, then it's very important that we remove this u vertex from the queue, so that's why we have to reconstruct the heap, and it takes logarithmic time complexity. Then, for each neighbor of u, the temporary distance is equal to the distance to u plus the distance between u and v. And if the temp distance is smaller than the distance v, then we reset the distance v to be equal to the temp distance, and the predecessor is updated. So basically with this for loop, we check whether is there any shorter path to the given vertex. So that's why we get the u vertex from the queue, and we check that for every neighbor of u, we call it v, are there any shorter paths? And if the temp distance is smaller than the distance v, it means that yeah, we have managed to find a shorter path, and that's why we update the distance for the v to be equal to the temporary distance. And of course we have to update the predecessors as well. Then there's the last line basically, that's we have to return the distance. Okay, so we return with the distances. So basically what's very important as far as Dijkstra's shortest path algorithm is concerned, that first we have to initialize the variables. We set the distances to be infinity, and we have to set the distance to the source where we are standing to be equal to null. Plus we have to construct a heap, and we have to add all the vertices of the graph to the heap. And then while the queue is not empty, we get the minimum distance, that's why it is a greedy algorithm. We have to remove this vertex from the queue, and we check for every neighboring vertex that, okay, are there any better solution, in the sense that are there any shorter path? And what is the distance? The distance, basically the distance to the vertex where we have been, so the distance u plus the distance between u and v. Basically it is the edge weight usually stored in the edges. So it is quite apparent, it is quite easy to implement Dijkstra's algorithm, and it is working quite fine. It is a fast algorithm, so it can be used in softwares, so it can have several practical use cases. Okay, in the next video we are going to see a concrete illustration of Dijkstra's algorithm. Thanks for watching.